All right, everyone. Hope you guys had a great weekend. This is the start of week 3, which is the final week of the coding bootcamp prep. This is going to be session 7. It is Monday, May 9th, about 6:15 Central Time. This session is going to be covering two concepts: truthy, falsey, and recursion. Truthy, falsey, you have already been running across inside a lot of your functions, even if we haven't specifically talked about the subject matter. So what truthy, falsey is that everything in JavaScript has a value. Only a handful of things have a falsey value, and that is false, the number 0, empty strings, null, undefined, and nan, which is not a number. Any other value in JavaScript has a truthy value. So a string with the number 0 in it is basically a non-empty string, so it's true. Even if you write false inside a string, it's just reading it as a non-empty string. That is also true. An empty array is true, an empty object is true, an empty function is true. Any combination of strings and variables, any way you can think of it, as long as there's a value there that is not one of these 6 values, it is basically going to return true if you do a basically just like check to see if anything is there. It basically comes back as truthy. And so where we run into that is there are basically, like, as soon as you do something that is a operator, or if we're looking for conditional logic, so like if you throw it into an if statement, we can basically use that value to either return false due to its falsy nature or true due to its truthy nature. So if I say let, we'll just do example equals 1, right? And then if I say if example right? So what we usually see in an if statement is basically like, is something equal to 1, right? So if I do this, right, that gets truthy because that's true, right? So if I do this, now it's basically, it's not falsy, it's false. But we can put just a variable there, right? And then we can check against this truthy or falsy nature. So if I do this, it's truthy. If I do this, it's falsy, right? And so 0, null, right, is falsy. Undefined. So remember, this is a 2-step process. This is instantiating my variable example, and then this is assigning my variable example the value of null. So if I don't assign it a value, it's undefined, right? So that's falsy. And just to prove it that it's undefined, we can say console.log example. Right, and see, we get that undefined right there. So when you don't assign a value, you just instantiate it, you bring it into existence, but you don't give it, you don't define any value. It is undefined by default. So, and same thing, like we could do null, right? But it's a string. So all it sees is a non-empty string. So that's truthy. Right? But if we have an empty string, right, that's falsy. It doesn't, there's no difference between the double or the single quotes. Right? And Same thing. It said that we could even look at doing it as a empty function. So I could say, let's do it the old way, function, example, function, right? So that's completely empty. But if I put that in here, see, it's truthy. There is some value in memory for it. And so the only way you are going to get falsy is if it's false, 0, empty string, null, undefined, or not a number. And this is used quite a bit when you start getting into like things like web development frameworks like React, where you're displaying something to the screen. And you can basically do what's called a short circuit, where you can use the falsy value, so the absence of something. So if it's not there, it won't render a blank space to the screen, it just renders nothing and it skips over it. So truthy and falsy is a concept that you will run across as you continue to learn to be software developers. Any questions on truthy or falsy?
I'm sorry, can you just kind of say again, so why would you use that as opposed to just using like the triple equal or like the strict equal if you're trying to bring something back?
Basically because it's basically it's just less code. So you could, but you don't need to, right? So I could say, like come back to here and say, is this equal to null? Right? And I can run this and I'll get truthy because it's null. Like if I don't want it to be, like if I want it to return falsy, you're basically, and if you want a specific outcome to happen when it's null, then you can be more explicit. But if you want to basically take the same action on any of these, if it's just falsy, then you're better off just checking for the truthy falsy and you're writing less code. Because right now, if I want it to do something, if I get anything that's falsy, that is not the same as this. Like I would have to do basically chain it all together. An example, for example, to undefined, right? Or example equal to 0, right? And so it's just easier to do this, right? And just get everything based off that one.
That makes sense. Thank you.
Yep, no problem. And again, some of the like concepts like addition and subtraction, like those are things that even if you've never developed software before, you have a working knowledge, some experience with it. Like when we start getting into some of the more, I don't want to say pure, but like more specific, like programmer only terminology. Like I don't know. I mean, you like in my head before I knew this, like if I'm thinking the truth, like you're telling me the truth, if you're sort of being truthy with me, then you're probably lying to me, right? Like, but so truthy and falsy are like computer science concepts that are basically having to deal with the inherent truth or false built into specific like instances that JavaScript will run across. And this is the way that JavaScript is written, right? Like when the guy that was inventing JavaScript was doing that, whatever, 30 years ago now or whatever, he could have said zeros by default were truthy, right? But like this was just under the hood decisions that were made at the time that the language was created. And there's almost every language will have some concept of this. I do not have a like authoritative list of what is truthy and falsy in each language. Like if it lines up the same in each language, or maybe in certain languages, like a 0 would still return like a truthy value, but it's out there, and it is something that you will run across as you, again, continue to learn JavaScript and become a web developer. All right. Any other questions on truthy and falsy?
So the whole term truthy and falsy just stands for true and false, and you're using that and console.log to highlight that true and false is what's being returned inside the computer, right?
Right. What truthy and falsy is basically boiling down to, because again, we are like, this is a variable, but we see the variable name there, but the computer sees what the variable actually changes to, right? So if I put a string hello in here, what happens down here is I'm actually getting if string hello, right? And I am not comparing this against anything, right? I'm not saying is it greater than, I'm not saying is it equal to, anything like that. So it is literally just saying, does this string that I've just been given have a truthy value or a falsy value? And if it is not one of these 6 things, it is always truthy. Right? So at the end of the day, what this eventually boils down to is this. Right? So it goes, we're feeding it if example as the variable. So the computer says it sees the variable, then it goes up there and checks that what's the value of the variable. It's the string hello. Okay, so now the computer is seeing if hello as a string, and then basically that eventually reduces down to true. Right, and if we were to do the same thing, so let example 2 equal, or we'll just leave it undefined, it would boil down like this. It would say if example 2, which then turns into if undefined, which would then turn into if false. Right, and so and that's part of this, is that when we feed in, whenever we use a variable or a parameter, that is just a placeholder for a value that we're actually giving it somewhere else, right? So when we do it as a variable, and same thing, like if we were to come into here and say name, and just say console.log name, right? And then I come down here and I do example function Charles, right? When I console.log out, I don't see the word name over here. I see the string Charles over there, right? So there it is. And so wherever you see name, that's how it starts off. That's how we write the function so that it's reusable. But at runtime, when I hit run and I call this function into existence, all of these names are basically, the computer sees it like this. Right? And it doesn't matter how complex the function gets, anything like that. It's basically, and we're just using parameters and variables as placeholders. Does that help? Does that help draw a little bit clearer?
Yep. But the other question was why truthy, and why do they call it truthy and falsy? I've always just heard true and false.
So because it is not true or false. Right, like it is having to deal with the inherent assigned true or false assigned to it by JavaScript under the hood. right? Like all of these values will result in a false, but like 0 in itself is not false, right? False is the only thing up here that is actually false.
Okay, I get it.
Yeah, and so that's why it's not false, it's falsy, right? It's false-ish. And so it's just giving it that inherent value that's assigned to these values by JavaScript. So, and like I said, I know it's like a little bit of a confusing concept, but what it comes down to is like, this is what it is, right? Like, there's all sorts of jokes about JavaScript. I mean, it was like the heyday of the internet in the early 90s or whatever, and they basically invented a language in like a week and a half or something like that. And like and I don't think energy drinks existed yet. So it was basically like the running joke is like, how much cocaine did like the founders of JavaScript need to be on to be able to crank this language out in a week and a half? And it's also now going on 30 years old and still being widely used. And I mean, outside of say JavaScript and like Java, there aren't a whole lot of languages that have had this much usage, but also for this long, right? And just as I mean, look at anything else humans do, like the longer it exists, the more people that are involved with it, like the more weird things tend to get bolted onto it over time. And we do our best to keep like organization and standards and practices, and there's a whole council of like non-mortal developers that basically decide what's going into the next version of JavaScript every few years. But there's going to be some weird things in here, and there's going to be some weird things that are maybe they weren't weird when they were written 30 years ago, but they're weird now. But that's just the way long-lived computer languages end up turning out for the most part. All right. Anything else on Truthy or Falsey or life?
Can you show your code again real quick?
Sure.
I don't know why when I typed it in, it's just returning like nothing. It's just blank.
Are you console.logging?
Yeah, I wrote let example equal, and then I just put empty string, and then I said function example func parentheses. So the parentheses I can leave blank on line 6.
Well, if you're not feeding in a parameter to console.log, you see if name's here, it has to be here.
So, oh, I didn't do a console.log. I went after function, then I said if example, and then did console log, else console log.
Is your if block inside your function?
Yes. Let me show.
I've just got the if pulled out at the global scope, because if this if block is inside your function, if you're not calling your function, nothing will happen.
That's why. Okay, thank you.
Yep, no problem. All right, anything else in here? All right, recursion, time to bring the pain. So recursion is the process in which a function calls itself. Using recursion to solve a problem requires 2 cases. A base case, the condition at which the function stops calling itself, and a recursive case, the case in which the function returns itself. So we've got an example function here, sum up to, and we can go ahead, we'll pull this over. This stuff out. All right, let's go ahead and sum up to 5. sum up to, find sum up to, sum up to. What am I now? Sorry,
Just
what's that?
Dump up to.
Oh, there you go. All right, so 15, right? So 5 plus 4 is 9, plus 3 is 12, plus 2 is 14, plus 1 is 15, right? And so in normal terms, right, if I wanted to do that, so I could say function sum up to here, and we could do while num is greater than 0, result 0, result, oops, sorry, result plus equal num, and then num minus equal, I'm sorry, just num minus, yeah, minus equal 1, I believe. We'll see what happens. And we'll return result. Let's do console.log sum up to, we'll do 5. Let's see what we get here. We get 15. All right, so let's take this over to Python tutor. All right, so this is the way that we're used to doing things here. This. All right, so here's our function that we've created. So we load it in, we come down, our first step is to hit our function call, and we come into our function, right? So num is now 5. See how, like I said, the parameters go away. Like num doesn't actually exist, only the number 5 does. We just use num to keep track of the number 5. All right, and result is 0. And we say while num is greater than 0, we'll basically keep doing this. So result plus equals num. So there's result is equal to 5. Num minus equal 1. Num is now equal to 4. Num is greater than 0. So we come back into the loop again. Result is now 9. And num is now 3. Right? We do it again. 12 to 14. 1. Result is now 15. Num is now 0. This is now false. And we come down here and we return result, and the return value is 15. All right. This is standard functional iteration. This is what we've been learning thus far. This is typically how you would solve a problem in the real world. This is basically giving us the exact same answer, but we're going to do it recursively. And it's going to look very different. If it'll even load up for me. This shouldn't be overloading it. There we go. So we're only doing this one in 16 steps versus 21 steps on the other one, or 20 steps on the other one. But watch what happens. All right, so we come here, our function is loaded into memory, right? And so we come down here, we call our function the first time. Sum up to 5, excuse me. So num is now equal to 5. And if num is strictly equal to 1, then return 1. Else, our recursive case, return num plus sum up to num minus 1. Right? So now, and notice how this is being called as a function, right? So before we were saving it as a variable, this is showing the function call. So now I've called the function a second time, sum up to, and num is now 4, right? And we come in here, it's not, 4 is not equal to 1. So we come down here and we basically add num, which is now 4, plus sum up to num minus 1. So we're calling num sum up to a third time with the number 3 in it this time. Right? We keep going, 2, and then finally, num is 1. So here's our base case. So the base case is what we're always trying to work towards, because if we don't reach our base case, it's just like writing an infinite loop. It's an infinite recursive call. So num is strictly equal to 1. So we're going to return 1 out of here, right? So notice that we hit this line. Return is the last thing a function ever does, right? Like no code underneath the return is reachable, right? So we hit that, and basically there's our return value is 1, right? And so that returns, and now basically we did going back up the recursive chain now, right? Now we've got 2 plus 1, and now our return value is 3. So our next recursive call we're going to take care of is going to be 3 plus 3. Our return value is 6. So now we're back up to this function call, and we're going to return 4 plus 6, which is 10. And now we're at our very first function call where num was 5. And we're going to, this is going to be 5 plus 10, and we're going to return that. And our return value is 15. And that's the end of our recursion. And that was a lot more explaining to do than just the loop, right? There's more things to keep track of while we're doing this. And that's why I said this is typically the more difficult way to do it. And the other issue is that this function takes up a chunk of memory. And each time we call it, it takes up another chunk of memory. So in this instance where we had to call it 5 times, where when we did it with the loop, it only took up 1 chunk of memory. This one took up 5 times as much memory, basically, to do it. Now, imagine if I summed up a number to 1,000,000, right? And if we had to do our loop, we're going to iterate through and count down from 1,000,000. But that number of 1,000,000 is just a number that we have to hold in memory, right? And then it's being added to the result, which is a second number in memory. So it doesn't matter how large that number is to a point. There is a specific point where like it will kick over and start taking up more memory if you give it so many decimal places. But for what we're talking about, it doesn't matter if we're going to sum up a number iteratively, which is using a loop, either if we're summing up to 5 or if we're summing up to 1,000,000, it's basically holding about the same amount of memory. And if we were to do this, sum up to 1,000,000 compared to sum up to 5, it would basically be 200,000 times the memory allocation. All right, and this being on like a virtual thing here, if I do this, it should tank it out. And even when I hit the button to visualize the code, and because what this website is doing is running through all of my code, it's actually running the program, and then it's going to break it down, right? Due to massive traffic overload, some requests may crash. Please wait and try again. So basically, I gave it enough to think about where it gave up on me. All right, so questions on this?
I have a question. What makes this a recursive function? Is it the fact that the function is included in the final return line itself?
Yeah. So it is, this is the recursive case. So when a function calls itself, it is considered recursive. Right, and it does all the same things that we do in a loop. It
Okay.
just does it without having
That
to
makes
physically
sense.
write a loop. More questions on this? Right, and see, now that I'm counting from 100, notice how we went from at counting to 5, there was only 16 steps to complete it recursively versus 21 in a loop. And now we're up to 301. And if I go back to this, oh, 305. So it's about the same. But what's happening is I'm only calling this function once, right? And then as I move in, see how I've got my function call one time here, and then I'm just keeping track of these things, right? Versus the other way, every single one that we do is a new block in memory. Right, and I can grab this and flip through it here. And so if we sum up to 100, right, 50 basically is the number that it comes up to. But notice how it was only called one time. There's just that one block of memory that's being used up for it. Any other questions on recursion? All right, let's visualize it another way here in the slides. So this is what we're seeing, right? So when we call sum up to 5 with 5, right? So num goes away. Everywhere where we had num is 5. So the first time we call it with 5, sum up to 5, right? We say if 5 is equal to 1, then return 1. But that is false. So we come to the else case. So we return 5 plus sum up to 5 with 5 minus 1. So our second call depth is sum up to with the number 4, right? This is false. We come down here, so return 4 plus sum up to 4 minus 1, right? And so that's 3. So we come down another level here and sum up to with 3. 3 is not equal to 1. So that's false. We come down here and we call 3. This now becomes 2, right? And then this now becomes 1 at our fifth call. So we've got 5 functions in memory right now. And this hits the base case, right? And so this returns 1. So this changes from sum up to 2 minus 1 to just the number 1. And so we return 2 plus 1, which is 3. This changes into just the number 3. And so we return 3 plus 3, which is 6. This is now the number 6, and we return 4 plus 6, which is 10. And this is now the number 10, and we return 5 plus 10, which is 15. Right, so when you do recursion, you're recursively calling down each level until you hit your base case, and then you return back up that basically call stack until you get to the top level and you return your final answer. Right, and that is pretty much it for the slides for tonight. We will cover some of the recursion problems in here today. I will cover the first one as a class, and then we'll see how we feel about breaking out into groups. If we don't break out into groups, I don't know that I'll have enough material tonight to take it all the way to 9, because usually when we break it out into groups, I'll give you like 20-30 minutes, and then we come back and I solve it, and that takes like another 10-15 minutes to explain everything. But if I'm just going through and solving it, then I mean, we may be done a little bit earlier. And I don't say that to like convince people like, hey, let's get done early. I'm just saying, if you want class to go the full 3 hours tonight, because I don't want anyone to feel like they didn't get their full 3 hours, then we'll need to probably split people into groups. Or you guys are gonna have to start asking a lot more questions, because we're moving pretty quick right now. And the like superhumanly quick through most people's first delve into recursion here. And I do apologize because I am rusty. I have not had the chat open. So let me just double check the chat here real quick. I don't know that you'd use recursion. Well, you can use self-replicating. So yes, you can use recursion to crash an SQL server, but if they're running an SQL server at this point, they're not protecting themselves from injection attacks. You might as well just do select star or delete from select star, which will basically just take everything in that database and delete it in one command, which is way meaner than crashing it and then letting them figure it out and bring it back up and they still have all their stuff. But you can definitely look into, if anyone has any interest in hacking or like basically like white hat hacking or pen testing or anything like that. Some of the more modern self-replicating Trojans are definitely using recursion, where they're basically breaking into a system and then they're building copies of themselves and then installing copies of themselves in different directories. And they're basically just iterating through, so it becomes much more difficult to delete all of them out. That would probably be like a use case for recursion. So since recursion uses so much memory, could you provide a real world example that would be better use for iteration or use for recursion? Okay, I'll wait to hear back on that, just some clarification. Okay. For real world use for recursion, there typically isn't one. Like I said, using recursion in modern software is going to be a niche role, right? Like if you're going to be doing data science and using Python and pandas or MATLAB, and you're basically like iterating or recursing through data sets, that then you would use recursion. But like I said, in modern web development, there isn't a case for using recursion. Why we cover it is because like this is a big topic in like computer science programs. Like you will learn recursion if you get a degree in computer science. And because this is a popular interviewing tactic, which again, for those of you that are familiar with military culture, there's that thing called hazing, right? And some companies are doing a better job of interviewing than others. But why does anyone get hazed in the military? It's because the person doing the hazing most likely got hazed as well, right? Like my corporals beat the snot out of me, so I'm going to beat the snot out of you, and their corporals beat the snot out of them, and that's why the cycle continues. And it's the same thing with tech interviewing. Like you will get so when I lead tech interviews, I give you a functional problem to solve, right? Like, which is convert bad CSV data into JSON and use tests to incrementally improve your process, right? Because that's, even if you're not converting CSV to JSON, what we're doing as developers is taking data from one source and processing it and either storing it or displaying it. And we have to manipulate the data to be able to accomplish that. So to me, I feel like that is a fair problem, because that is, you will be doing something similar in your work. There are places that still do interviews where they'll ask you things like, okay, right, like reverse a string. Okay, now reverse the string recursively, right? And knowing how to do recursion basically tells them that you probably paid attention in CS 101, but you'll probably not be doing any recursion at all in your day-to-day work. So I don't like questions like that where I'm asking you to demonstrate something to me that you don't need to do, right? Or like, especially like if you start applying to some of the big, like the FANG, so like Facebook, Amazon, Netflix, Google, and they start asking you some really crazy questions, and like dealing with linked lists and how to traverse a doubly linked list and stuff like that. And you may do something like that as a senior developer or on a specific team there, but like as a general interview question, it's not necessarily the best question. So I like questions that are slated towards proving to me that you know how to do what I'm actually going to be asking you to do in your day-to-day job. But we teach it because you'll get asked it at least once, right? Like you'll get the interview question or the take-home question, or they typically won't even give it to you in a take-home question. It's more of a to trip you up on the spot, and or like while you're whiteboarding to explain what's happening, just so that you demonstrate proof of the concept. It's just like another term that you'll run into, which is big O notation, which is basically tracking the growth of your iteration through your algorithm. So, and like you can basically have like constant and exponential growth in the amount of memory that your algorithm takes to do it. And there's more efficient ways and less efficient ways to write algorithms. And they'll touch on big O notation in Code Platoon, but it's also one of those things like the day I walked out of Code Platoon, I still had no idea what big O notation was. Like I knew what it was. I knew that it measures like how efficient your algorithm is, but I would have a hard time telling you what the efficiency of the algorithm is. And 3 years since then, I've not had anyone tell me like they're asking me like, what's the big O notation on the algorithm you've written to solve this problem? Like it just, but knowing that there's more efficient, less efficient ways to do it. Like every time you nest a loop inside a loop, your algorithm gets slower. And if you've got 3 nested algorithm or like three levels of nested loop, you actually can run into structural problems with your algorithm where fairly small sets of data. And when I say fairly small, and like I said, I mean, my set of data is applicants that are joining the military. And in a year, I think we've created close to like a little over 1 million records, right? So if I set something that has to iterate through all 1 million records and nest down 3 times, right? Like that first one is going to go to the first one to 1 million. So I think at that time, like worst case scenario, if I had to iterate through all of them, I'm basically iterating through 1 million times 1 million times 1 million, which is a lot. And like that would get really slow. So there are practical concerns to stuff like that, but it is something where like knowing the actual like computer science definition of it is not outside of getting asked an interview question, it's not like a strict piece of knowledge that you need to know. And it's the same thing with recursion. All right, so let's see here. So let's go ahead and take a poke at pyramid. And can you guys still see my screen? No.
Yeah.
Okay. We froze there for a second. All right, so you can still see the pyramid replet, right? Cool. So, oops, let's do this. Let's go ahead and fork it. All right, so instructions. Using recursion, write a function that returns the total number of blocks in a pyramid with a given height. A pyramid looks like this. 1, 2, 3, 4, and or 1, 3, 5, and 7. So the number of blocks for a row equals 2 times n minus 1. Now, I'm not going to worry about entering in all the spaces and everything like that. I'm just going to basically return the correct amount of asterisks in each row. So my pyramid will be a little lopsided here. Well, actually, it's not even asking us to return that. It's just saying returns the total number of blocks in a pyramid with a given height. A pyramid looks like this. So pyramid of 3, the answer is 9. So if we look at, we have one input, a number, and our output is also a number. All right. So the number of blocks for a row is 2 times n minus 1, right? So if we did this 3 rows, so that first row, 2 times n is 6, minus 1 is 5, so that first row is 5. The second row is going to be 2 times 2, which is 4, minus 1 is 3, and 2 times 1 is 2, minus 1 is 1, right? And then 1, 3, and 5 is 9. So when we do recursion, it's important to identify your base case. All right, so if you never reach your base case, you will, it's basically like writing an infinite loop. You'll just keep recursing and recursing and recursing. And a loop will run out of memory eventually if you let it run. But like recursing will run out of memory typically much quicker, but you end up with the same thing. So when do we want to stop recursing? What do we think our base case is?
When 2 times n minus 1 equals 1.
Okay, so basically if height equals 1, so it's not the necessarily the 2 times, I mean, in this instance, 2 times n minus 1, if you do 1, that does equal 1, but basically it's when your row reaches a height of 1, right? Because we're going to keep feeding in, just like we did in the notes, we're going to keep calling height, or we're going to keep calling pyramid with a height that is slightly lower each time until we get to a height of 1, right? And so our base case is, oops, when the height is equal to 1, we're going to return 1. Else, we're going to return it's going to be 2 times height minus 1 plus our recursive function call, right? Which is going to be height minus 1. All right, so let's go ahead and give this a call. Let's do pyramid 4. And that should give us 7 plus 9. So we should get 16 as our return. And there's our 16. So let's go ahead and take this back over to Python Tutor. Oops, sorry. All right, so again, here we come and we load this into memory. There's our function. All right, so we call pyramid with a height of 4. So this is we check against our base case. 4 is not equal to 1. So we come to our recursive case, which is basically 2 times 4 minus 1 is 7, plus another call to pyramid of height of 4 minus 1, which should be 3, right? So there's our next method or our next function call, and height is now 3. And we keep iterating through. There's 2, and there's 1. So there's a height of 1, right? So here's our base case. If height is equal to 1, return 1, right? So now we return 1, and this becomes basically the return value of 1. So there's our return value of 1. Return value is now 3 plus 1, which is 4. Now our next one is going to be 4 plus 5, which is 9. The next one is going to be 9 plus 7, which is 16. Right, and then that is our final return. And because I left the console in there, our final return value is 16 off of our last call. All right, any questions on that one?
I guess what I'm not getting about this is, all right, I understand how it calls itself until you get that 1, but I don't understand how, like I guess in Python Tutor, how it's working its way back up, like where exactly we're at there. Is it executing all the way down to, like, it hits height is equal to 1. So I guess I don't understand why it doesn't just give you 1 and that's it.
Okay, so and this is more of a slow motion conceptual thing, right? Because when the computer runs it, you see the end result of 16 instantly, all at once. But what's happening is, so again, the same thing, like sum up to 5. The last thing that ever happens in a function is the return, right? So all code below the return never gets executed, right? This is on the return line. So what's happening is basically we come in here, sum up to 5, we check against the base case. 5 is not equal to 1, so we do not return 1. We come down to the return case, which is return. It's the last thing that this function will do, and it's going to be 5 plus this function call. And this is why recursion is so memory intensive, is because I now call this function, right? And we're showing it like this, but in reality, like they're all one right after the other, right? And so what we're actually seeing when we do sum up to 5 is it actually looks like this.
That's your M1s, your M1s, your M2s, your Apaches, your ADA, your what else?
All right, so it's literally 5 plus
Okay, I think it makes sense. I think it makes sense just on that slide, how it was like, I guess the first time I just didn't visualize like how it's all like nested in itself, like the steps kind of make sense, I guess. If I think
Right.
about it like running down instead of
right.
like
This is
somehow
basically-
working its way back up, which is just how Python tutor was showing it.
Well, and that's the way the computer looks at it. So
Yeah,
you have what's called a stack, and you basically are stacking these functions on top of each other in memory. And then once it's done, so like once you're done stacking things, it then looks at the last case, right? So sum up to 1 is our base case, and we know that this returns to 1, right? And then this is going to return to 2, this is going to return to 3, and this is going to return to 4, right? And that's what happens. But and it happens quickly, but it doesn't matter how quickly the computer does it. It is still following a specific set of instructions, like it is doing it in order. And what's happening is basically we keep going, and every time we call the new function, basically all of this gets held in memory until we get to a point where there's no new function being called, right? So when we hit our base case, it's just a return. And this turns into 1, and then this turns into basically like 3, 6, 10, and 15.
Yeah. Yep.
Okay. Yeah, and like I said, don't worry about it. I mean, like recursion's definitely a different way than like the way we normally look at things. So all right, any other questions in there on what's happening? Let's see, what's the next one on the challenge list after pyramid? Pyramid, and then it's reverse word. Okay, so with this one, instructions are using recursion without creating any additional variables, create a function that returns the reverse of an inputted string. So hello would be hola, and it looks like we are keeping like we address punctuation, we keep capitalization, like we don't have to do anything crazy with that. Let's see here. It is 7:13. I've got to put some eye drops in. So why don't we take like a 10-minute break here, and then we can get back to it at 7:23 unless there's any other questions before we go on break.
Could you just show me that, the last one, the pyramid one real quick?
Yes.
I just wanted to read that other comment. Okay, thank you.
All right. So I'll see everyone back here at, we'll say like 11 minutes. We'll see everyone back here at 7:25.
Yeah, Charles, to the comment that was just, oh, done.
No, go ahead. I'm still here.
You might want to disconnect and reconnect because you've been coming in and out the whole time. It's not too bad, but
Okay. Yeah, I saw I had a couple of internet stable pop-ups. The only thing I'm trying to avoid is that if I disconnect and reconnect, I think it'll stop the video altogether. Let me go see if I can shut something off. I may just have to shut my video off too, and that might help. Okay, so with pyramid and the sum up to, both times, we're working with numbers. Recursion works for strings. You can basically use it for anything that you'd use a loop for. So let's go ahead and take a look at how we would solve this reverse a word. Now, what we're going to need to do here is basically determine what our base case and our recursive case is, right? So we know we have input is a string and output is also a string. All right, so we need to identify two things here. So we need our base case and our recursive case. So does anyone have any idea how we would go about moving towards a base case, or what our base case might be?
So I want to like turn it into, well, actually, we don't really need to turn it into an array, do we?
Nope, we don't want to turn it into an array because I think it using recursion without creating any additional variables, create a function that returns the reverse of an inputted string. So without being able to assign it to a different variable as an array, like we wouldn't be able to turn it into an array this time.
Okay, so in that case, I want to, like, I think we have to split it, right? To be able to like look at them all individually somehow.
Well,
So I want to say like, if it's, if word dot split 0 or whatever, word 0 dot split, I don't know.
so dot split is what changes a string into an array. So we wouldn't need to do that, but you're right that we need to start looking into built-ins. So let's take a look here. So we don't want to use dot split, right? So split method divides a string into an ordered list of substrings, puts these substrings into an array. So we don't want that. Something that would be useful though is right next to it, and that's slice, right? So the slice method extracts a section of a string and returns it as a new string without modifying the original string. All right, so if we take a look at that, so let's go ahead and pull that. Sorry, here we go. So let's see what happens when we do console dot log hello. Right, and so the index of the beginning of the specified portion of the string, right? So if I don't put anything in, right, it gives me the whole thing. And if I put in 0, it gives me the whole thing. If I put in 1, it gives me everything but the H, right? And so now if we were to do console.log example, remember strings have index positions just like arrays do, right? So now I've kind of determined how I would split this into two sections, right? And so now what I could do is when I recursively call my next reverse word in the recursive case, I could pass in example slice 1 over and over again, right? Because basically that is LO, right? And so, and then the next time around, it would chop off the E, the next time around, we'd chop off the L, right? And then we're also holding that in the index position. And the only thing I'm not clear of is if I have to return it in a specific way, but we'll play with that and we'll figure out which way is the right way. But that means that if we're going to keep passing in the string that with one less character on it, what do we think our base case would be then?
Maybe just empty parentheses,
Bam.
essentially nothing.
An empty string is I think is going to be my base case. So I would say here for my base case. So if in order string is equal to that, return that, right? So that'll be the last thing I do is I'll return that empty string, and that's going to fire off the chain of events where I'll start returning the rest of the words, right? And so now my recursive case, right? So we'll say, oops, else and we could say return, and notice how there's always two return statements in here. We've got to call our function. And again, I don't know if I need to do the function first or the in order string first. So we'll try it this way first. And if that's not right, then I'll just have to reverse it. So we'll say in order string dot slice 1, and then we'll do that in order string 0. All right, let's go ahead and change this to hello. Let's comment this out. Type error in order string slick. How about slice? Oh, and we've got to wrap this in a console. It's very anticlimactic of me. So there it is backwards, right? And I think if I were to do it this way, it would probably just give me hello again. All right, so yeah, it is order determinate. So there we go. If we add in some spaces, right, it keeps going. So let's go ahead and take a look at this. All right, so 19 steps. So we come in, we load the function into memory, we get down here, we call the function, we hit our base case. In order string is equal to hello, is not equal to an empty string. So we'll skip over our base case, we'll go down here, right? And now we see we call in order string a second time, missing the H, missing the L, missing the O, right? And now basically we're here, in order string's been called with an empty string as the parameter. That should trigger our base case, right? And so there it is. So there's our return. And now it's the empty string plus the letter O, the empty or O plus L, OL plus L, plus E, plus H, right? So we worked our way down the call stack. We hit that return. There was no more functions keeping everything open. So we start returning back up the stack until we get to 0. And we get to our base, or until we've basically gotten to our first layer, and that returns, and then we're done. Any questions on that one?
No questions, but can you do the whole thing again? My brain's slow to catch up.
Yeah, absolutely. Do you want me to do it in Python tutor? Do you want me to draw it out in the Replit?
No, right here in Python tutor is perfect. Just
Okay.
just do it one more time. Thank you.
Yep. Yeah, so again, when we turn our program on, right, we take reverse word as a function, we load it into memory, right? It's not doing anything. We haven't given it a parameter. We haven't told it to activate yet. We come down here to line 11, we call reverse word and we give it the parameter hello. All right, so in order string is now equal to hello. So wherever you see in order string in here, it is the word hello, right? So hello is not equal to an empty string. So we skip our base case and we go down to our recursive case. Our recursive case is to return another function call, a recursive function call to reverse word again. And we're going to call it with hello with starting at the second index, right? So we're chopping off the 0 index, which is the H, right? And so we're calling in order string a second time with just hello, right? And we're holding the H right here, right? The next time through, we're holding the E right there, the L, the O, right? And then eventually we get down to our empty string. And that will return true against our base case. So this is now true, and we return this. And so basically, we don't come down here. We're done with the recursive case. This becomes an empty string. And now we start going back up the call stack, right? So on the next one, right, so there's our return value. So our return value off this one is now basically empty string plus the letter O, which is being held here. And we're going to return that up to this function, right? And now it's going to be the letter O plus the letter L, right? And that's how we get the OL. And we return that up to this function, and it becomes basically the letter O, or the letters OL plus the letter L, right? And there's our return value. And we pass that back up to this calling of the function, and it becomes OLL plus the letter E, right? And so there's that. And then we return it up to this function, and this is our last one, and it becomes OLLE plus the letter H. And then we return that out of there, and that's the last layer of our stack. Did it help that time a little bit more?
Yes. So yeah.
Okay, and let me do this too. So basically, like for our recursive cases, as we work through this, right? So we're going to return right? And so each time we called this and we sliced off the first letter, and then we hold the first letter over here, So we have this, the first call, the second, or this is the second call. The first call is this. All right, and so we call this down here. We come in with, this is our recursive call. This is our return, which is basically the H has been sliced off. We're starting at the first index position or the second index position. And then we hold H, which is the 0 index position over here, right? And then we keep going all the way until we call it with an empty string, and the empty string is our base case. And so we return this, let's just say, right? So this at our last call returns this out of our base case. So this becomes that. And then this becomes that. And then this becomes that.
Shells, I have a question after you're done.
Yep, one sec. Right, and so this is going down, and then this is how it gets passed back up. And then we can't return anything else from there. And Chris, did that answer, is that helpful, or do you have any more follow-ups on that one?
Nope, that was it. Thank you very much.
Okay, Yazid?
Yeah, what I'm not understanding is why is it coming back up? We hit the return empty already, so why is not just getting out of the function? That's what I'm trying to understand from the recursion part. I'm still not understanding.
So it basically, it is when we do this, right? So because we have a return, but we have another function call, right? And so this function has to resolve itself into an answer. And each time we do this, even though there's a return, there's a function. And until we get to here, right, this is the base case, right? When we get to calling reverse order with an empty string, that is when we no longer make any recursive calls.
Exactly. So, but at that part, why is not coming out of the function when we hit the base case? That's what I'm not understanding.
We do come out of the function once we hit the base case, right? So, because once we hit the base case, this result, so all of these return for practical purposes, they all return at the same time, right? But for demonstration purposes and like conceptual purposes, they return in order, right? So this one returns an empty string, and then this function call basically turns into two values, right? An empty string and an O, and it returns, right? And it just keeps rolling uphill until you can't return anymore. But as long as you're calling another method, you are going to leave all of these open until the last method you call resolves itself into basically a non-method answer, right? Which is what our base case does.
So basically the last line of the function that we have right there is return empty. That's the last line that the code executes, right?
Right. This is the last line of code that will execute,
Okay.
right? For the base case. But this is technically the last line of code that executes for all of these calls up until the base case. Right. I
But
know it's a little confusing.
Each return on the recursive case will console log something out on the screen.
Right. So
no.
like I could do this, right? So I could say console.log recurse and console.log base, oops, base. And then if
You have a
we,
typo on console.log.
oh,
there.
thank you. I see it. And let's change this back to hello, just for brevity. Right? So there, I come into the function the first time in here. Let's do this. Let's do in order string plus recurse. Right? So we call it the first time with hello, we recurse. We call it with LO, we recurse. We call it with LLO, we recurse. We call it with LO, we recurse. We call it with O, we recurse. We call it with an empty string, we hit our base case. Right? And notice how we're not running the whole program again. Like we're not getting a bunch of recurses going back the other way. We've just hit all of the returns basically at once, and they all return up to give this, right? Like this is for demonstration purposes. Does that help a little bit, or are there more? And don't worry, I mean, ask questions. Other people have the same questions as you. So if you don't get it, just let me know and we'll keep picking at it. We've got time.
I'm understanding slowly now. So after your example, right, after the base, where is it said in the function that is supposed to return hello at the end, the last line on the console log out? You see where you say hello?
Well, that's because I'm console.logging my final return down here in the function call.
Okay.
Right. So if I didn't console.log this because I'm just returning a word, you would never actually see the reversed word.
Gotcha. Okay.
All right, and let me see here too. The best one ever on YouTube, huh?
What is up, people?
Oh, what is up, people? I like that he's on a repli. I like that it's only a couple of years old. And I also like that it's only 10 minutes long. So I will drop this into, I know, what is up, people? Don't forget to smash that like and subscribe. I will ask for kickbacks because I'm pumping his channel. How about that? I'll throw that in the chat, and then I'll also in the notes section for the evening, we'll do we'll throw that right there as well. And so that way, maybe even hearing it from someone else. And like I said, this is yeah, there you go. tell me if you use recursion in your day-to-day life. So, but no, that will just like hearing it from someone else. I'm pretty sure there's also in free code camp. I don't know if they do a recursion in there or not. JavaScript algorithms. It's JavaScript. Oh, look at that. Replace loops using recursion, use recursion to create a countdown, use recursion to create a range of numbers. So that is in free code camp in the basic JavaScript. So let me do this as well. Throw this into the notes.
Do recursions always need to count down to, I guess, either a blank or a zero? I don't know if that even makes sense the way I asked it, but
No, I see what you're saying, and they need to count towards a base case, right? And like I think zero is kind of like it's a way in our brain, but right, like you could set like a function that says like count to 15, right? And then keep calling it, and like the base case is like when num equals 15, stop counting, right? And like return through. I think you could do that, but as I think about it, maybe you couldn't. I don't know. Yeah, you probably couldn't. Like it'd get overly complicated because you return up, like you'd end up with like a much larger number. Let me just copy that, and we could take a look at something like that here real quick. 1 second here. So let's see, we've defined a function. The range of numbers with 2 parameters, the function should return an array of integers, which begins with a number represented by the start number and ends with a number represented by the end num parameter. The starting number will always be less than or equal to the ending number. Your function must use recursion by calling itself and not use loops of any kind. It should also work for cases where both start num and end num are the same. So this would probably be one where you could look at doing it without like having to count to 0. But I was just thinking,
in that scenario, it still has to go down though,
what's that?
I think.
Yeah,
It would still have to go down. So it sounds like it's always a negative.
yeah, like you're decrementing
Or
towards
rainbow.
something, which makes
Yeah.
sense because that is kind of like a finite case, right? I mean, in practicality, like you can't have less than 0, like you can have negative numbers, but like 0 is kind of like the natural stopping point. And the same thing with like an empty string, right? Like we're going to keep having to pass through something smaller each time. And so the act of doing that is what gets you to like that 0. And again, there may be cases where you do it, but like I said, I'm by no means a recursion expert. I don't use it in my day-to-day life. Let's see here. So we just did reverse word. Where did I miss one here? Yeah, and you could use recursion wherever you use a loop. It's just again, it's typically not the cleanest way of doing it. Okay, so here is Palindrome. All right, so this one's a fun one because this one will have a base case that's a little bit different than what we're used to. All right, so write a recursive function that takes in a string word and determines if the string is a palindrome. If it is a palindrome, return the Boolean true. If it is not a palindrome, return the Boolean false. For reference, a palindrome is a word that is spelled the same backwards and forwards. All right, so let's go ahead and fork this replit. All right, so we've got race car, conifer, help, evil olive. So it looks like we can add multiple words in here. So looks like we're getting rid of any white spaces. So that'll be an extra twist to it. Yeah, as far as the alphabet one and recursion, I'm sure it could be done. I don't know that. I'll take class time tonight to do it. But I'll take a peek at it. And what is the alphabet one that you're talking about? So the alphabet code one. That might be a little difficult, actually. You could use recursion to assemble the array. Well, yeah, I mean, basically you can do the same thing the way we did it with the string. So if you created a like a string full of the so if you created a string with like all the alphabet, the only problem is that, and yeah, you could do it. It's definitely going to be messier though. Trying to think of the base case. So the base case would be once the letter in the 0 index position of the array matches the letter that you have there, like you could stop iterating, but you would have to also keep track of how many times you've iterated in. So you would need basically a variable that gets added to each time you basically add it, and then you would only return that variable if the base case is hit, and every other time you would need two basically your two cases of return where you would return the variable that has kept track of how many times you've iterated in, so you keep track of the position where it was in the alphabet, and then every other return would have to return without modifying that number anymore. So yeah, it could be an interesting use case. Maybe I'll take a poke at it. I don't know if I'll do it tonight, but maybe Wednesday night and have it to show on Thursday. But also, again, it would be an instance where like using recursion would be a lot messier than just using like an appropriate data structure to loop through it. All right, so we have Palindrome. Do you guys want to break up into groups of say like 4 or 5 and take a stab at this one on your own? I'm not twisting anyone's arm. So if you don't want to, you don't have to. Not really. Okay. Fair enough. So basically, I just want to make sure that everyone's getting the most out of this that they can. So if me explaining it gives you the best bang for your buck, then we'll do that. But if you want to take a stab at it, and the other thing I'll always say is I post all of my solutions at the end of the day and the intro, but nothing saying that you can't go back and try and tackle these on your own after the fact. And also, I know I have had a handful of students reach out to me on Slack asking me questions. I try to answer as quickly as possible, but I do respond to everything. So, and one or two students out of a class that started off close to 40, like I said, if you've got questions and you need help or you want to run something past me, feel free to Slack me directly. Feel free to drop it into the intro to coding. I mean, we're here to help answer questions for you. All right, so let me do this. All right, so palindrome, we are basically saying if the first letter and the last letter match each other, then it's a palindrome. Well, if basically at a grand scale, the word has to be spelled the same forward and backwards. And it looks like we're not worried about spacing here. And then also there's something with this. Let's take a look at this as well. So palindromes can be both even and odd numbers, right? So race car is 7 letters long, but we could say 8-letter palindrome. Sneddons and Snellings, that's the best you got for me. How about a 6-letter palindrome? There we go. Pull up. Used to be able to do those. Oops. All right, so this one, we kind of stop when we're comparing 2 letters that are equal to each other. But in race car, right, like there's nothing to compare the E to. So these are both palindromes, but they're 2 separate cases. Let's see. Okay, so let's take a look here. So when we were doing the last one, we were basically grabbing 1 letter at a time. In this, when we're doing the palindrome, we basically need to do 2 letters at a time, right? Like we need to grab the first and the last letter. So let's go ahead. We know that we're going to be using slice. So let's go ahead and take a look at a couple of different things here. So let's just start with race car. All right. And so let's go ahead and do console.log. And we're going to do word.slice, right? And well, actually, I'm sorry. So when we're comparing them, we need to look at this. Well, let's see here. Well, I'm sorry, I'm getting ahead of myself too. So we have one input that is equal to a string, and we have one output that is equal to a Boolean, right? We're only returning true or false out of here. And so if we want to, let's see here. So before we get to any of this, like, let's think about what our base case is, right? And so our base case will be if word. So, and again, last time we did like if word is an empty string, right? But because we're going to be dealing with odd numbered words this time, we're not going to, like, we don't, it could technically be any one letter in the alphabet. So we can't really do an equality to the letter here. So what we could look at doing though is like word.length, right? And so if word.length is equal to 0, or word.length is equal to 1, right? So if we're going to go through just like we did with the last one, and we're going to start chopping letters off, and this time we're going to chop letters off at the beginning and the end, then we're going to either end up with 0 being the base case or 1 being the base case. And that will be where like those are our two possible outcomes there, right? And so when we do that, we can we're going to return a Boolean out of there. So we're going to return true. All right. So now we need to look at, let's see here, looking at how we're going to get the first word and the last, or I'm sorry, the first letter and the last letter. So let me see the chat here. So the issue is that every time we make a recursive call, we're not passing through the original word, right? So we could do that if we did like word in like original word, right? But as like one with the way of doing it recursively, the only thing I can pass in each time is the one variable, right? And so our base case is going to return true, and if we don't make it to our basically our base case each way along the line, we're going to have a false. So if I do this, true or false or true, what does that return? Returns true. Now, if I do true and false and true and true, what does that return?
An error, maybe?
No, it won't return an error, it'll return false. Right, and so we can prove it here, right? So we can say console.log that, and we can console.log that. Right, so that returned true and this returned false. So when we do or, if any of the values return true, it's true. If we do and, every single value along the way has to return true. All right, so if I am taking the first and last letter and comparing them and saying, are they equal? I will either get true or false, right? So like in race car, right? So I'm going to do and that's true, right? And I'm going to keep going all the way down until I get to E, right? If I do conifer on the very first round, I'm going to do C is equal to R, and that is going to be false, right? And I'm still going to recurse through and make all of my recursive calls where I compare each of them. But at the end of the day, just like when we did this, where I kept calling it and pushing it through, what I'm going to end up with for Palindrome is just a bunch of true and false statements, right? And so if I compare them with an AND operator, so I'm basically chaining through a bunch of true or false Boolean values with ANDs. If all of them return true, right? So as I iterate through, and basically this is true, A and A would be true, C and C would be true, and then E, because word.length is equal to 0 or 1, would be 1 in this case, that would be true. And then I would basically start returning all of my trues and falses back up through my call stack. And at the end of it, if I have one, it doesn't matter if I have 100 trues, if I have one false, I'll return false for that. Like I need everything to be true at that point.
Hey,
So
Charles.
yes.
Hey, did I miss the part where we explained the significance of the 0 and the 1? Like more specifically, the 1 being like the end of a string.
Well, so because we're doing length, right? And so let's take a look at this as well. Right. So
Is
if
length is like dot length like binary or something? It can only be first or last.
well, no, it returns a number, right? So if I do let word equal race car, right? So and then I do console.log word.length, I'm expecting 7, right? There's 7 characters in race car. 3, 1, 3, right? And so now as I recursively call, what I'm going to do is, so we'll just call recursive call 1. I'm going to pass in ACECA, right? And so console.log rc1.length, right? So now the length is 5. And then let our recursive call 2 is going to equal CEC. All right, we run it, so we get 3. And then on the next one, so for RC3, I'm going to pass in just E, right? Because I've already compared the two outside letters. I'm passing in what's left of the word, and my length is going to equal 1, right? And then I'm going to return true for that. And the same thing with pull up, because that's an even word at 7. I would do pull up and then ULLU and then just double L and then basically an empty string, which if I do empty string equal this. All right, that's a length of 0. So I'm either going to get down to 1 letter, which is the middle letter, or I'm going to get down to an empty string because I've gotten rid of both the letters and an even number of letters in a word. And either way, either one of those is my base case, right? And now my recursive case is basically going to comprise of two things. Recursive case needs to check the quality of the first and last letter of the word and make a recursive call.
So Charles, the 0 is simply the return for true. As you recurse through, you either are left with no letters for an even numbered palindrome or an even lettered palindrome, or you're left with one letter left over. There's an odd lettered palindrome, right?
Yep.
That's your base case. So
Yes.
you're establishing the base case. Okay.
Yep.
We have not yet written the recursive piece where it's chopping off the first and last letter, correct?
Correct.
Okay, I'm an idiot. My bad. I'm sorry if I slowed you down there.
No, no problem at all. And don't apologize. If you've got questions, stop me. Other people have the same questions. We can all take a breather, and I'm always happy to explain it again. So we're going to make a recursive call with the word less the first and last letter that have already been compared. All right. So what is that going to look like? So let's take a look here at a couple of things. So we know that slice gives me some different things here. So let's go back to just let word equal race car. And so let's go ahead and do console.log word slice, right? And so if we do basically we were doing word.slice1, right, which would give me the rest of the word there. So we have a start number and a end number, right? So the index is the beginning of the specified portion of the string object returns a section of the string. So this time we could start at the first letter and basically end at the second letter, right? And that just gives me R, right? And so same thing here. Remember when I was showing these the first time, we can use negative values as well to always track the end. So if we start at -1, right, we'll also get R. And just to show you what I'm doing here, if I do -2, that should capture E and R, right, or A and R, so of car, right? If I do -3, there's car, and same thing here. If I do 1 through 3 here, right, there's rack. So we've got everything except for the E in there, right? So if I do 0 to 1, so start of 0, end of 1, that is basically the first letter, and then that is the last letter. So let's take a look here. Conifer, oops. All right, so C and R, that shows that we've got that there. So basically what we could look at here is as a return, we could say is word.length triple equal, whoops, sorry, not word.length, word.slice 0, 1 triple equal to word.slice -1, right? And so if those two letters are the same, that will return true. And then we also need to then make our recursive call, right? And so when we are looking at this, oh, actually, I didn't comment that out yet. So this gives us, oops, sorry, let's return. So we were getting C and R. So the same thing here, console.log, word, slice. So if we start at 1, right, that gives us the onifer. And then if we end at -1, right, that's so that spells conifer, right? There's the first letter, the last letter, there's everything in between. So we could then say and here comes our recursive call to palindrome, right? And now we say, we're instead of just giving it word, we're going to do word dot slice 1, -1, right? And so that first time through, this would resolve to C to R, and this would be false. And then we'd call palindrome with basically onif in it, right? And then because we come in here again, and onif is going to have a length of 5, right? That is not equal to 0 or 1. So we skip our base case and we come in here and we do it again, and we're going to compare the O and the E, right? And then we're basically going to pass in palindrome with the word NIF in there, right? And that's a length of 3, not equal to 0 or 1. We're going to come in here, we're going to compare N and F, and then we're going to pass in an I, right? And then I is a length of 1. So this will return true. And it doesn't matter that this always returns true, because we have several falses that are going to get mixed in as we go back up our call stack. All right. So this, I believe we should be to a point where we're working. I haven't solved for empty spaces in here, and I don't know that I'm going to tonight. But oops, it was true. R is not defined. Sorry. That. All right. So true, 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 true. And so it's okay that these are all saying true because they wrote them as tests, right? So this is true equals true. This is true equals true. This is false equals true, which resolves to true. And then this is false equals false, and that also resolves to true, right? So again, oops, do this. What did I do? Oh, this one. All right, so true, true, false, false. So, and then this. It's false, and this should be true. And with that, let's see here. Yeah, and there isn't really anything in instructions if we should be treating that true or not. I could probably go in and strip out all white space, or I could say that because of the space, it's not one, but I'll ask Tom about that one. We can get that one cleaned up, but this would be the solution for this one. And so we can take this, and let's bring this one over to Python Tutor as well, and we can watch what happens. All right, so here we go. Load our function into memory, call our function. We have word race car. If word dot length is equal to 0 or 1, return true. That's our base case. Word dot length in this instance is going to be equal to 7. So we go in here and we basically call it a second time, and you see that both the R's are missing. And the A's and then the C's, and we get to E. So this now is hitting the base case. So we're going to return true out of here. So next return true, right? And now we're going back up to where we compared the C's. That's going to return true because C and C are equal. And then the A's, that's true. And then the R's, that's true. So I have what this at the end of the day resolves into is true and true and true and true and true. And so all of them are true. So we return true out of there. Now, if we were to go back and say, do it with conifer, right? So we've got here, well, it looks like that just returns false either. So it doesn't actually drill down into it and do there, which is fine because when we hit a false and an and statement, if the first part is false, then we do not even look at the other side of the operator. So if we did something where, all right, so if we did RE and then, which isn't a real word, but we'll go in a couple of times and then we'll fail on the O and the F. Right, so there's that. Then we pass in with the R's off there and we're comparing them with that. And then basically with the O and the F, that returns false. And then that's basically false, just keeps getting returned all the way back up. And that's the end of it. All right, question.
For line 5, at the end of it for the function, word dot slice 1 comma -1. Can you just explain what that does again? The 1 and -1.
Yep, for sure. So that is so slice again, and let's do this too. String dot slice. Let's drop this in here. All right, and so it's the same thing too. Like if we mouse over it, sometimes it does it, sometimes it doesn't in the replet. But slice basically is a method extracts a section of a string and returns it as a new string without modifying the original string. And the two different ways that we can use it is with just a beginning index or with a beginning index and an ending index. So, and we're using it both ways in here. So again, if we come down to here, right? So this will do all right, so in conifer, so starting at the 0, so again, like strings are just like arrays. They have indexes, they have lengths, right? So It is, and it should say in here that the starting is inclusive. Yeah, the index of the first character to exclude from the substring. So the zero base index to which to begin the extraction, right? So when we look at conifer, and so if we were to do this, right, we start at index 0, 1, 2, 3, 4, 5, 6. All right, so there's 7 letters in there. And there's 7 index positions, starting with 0, ending with 6, right? So we're giving it a start of 0. So start here at the C, and then the ending is the first letter to exclude, right? So we're saying 1, start excluding at 1. So all of this gets excluded, right? And so we just get that letter C. And the same here, we don't give it a ending because we're basically using negative indexing here, right? And so remember, -1 is the last letter, and -2 would be the last 2 letters. And so we're just saying, grab me the last letter, right? And so, and that is R in conifer. And then if we give it a start of 1, right? So we start including here, and then this R is the last one, or is the first one that we want to exclude, right? So we start counting here at 1, and we stop counting right before -1, coming back to this way. So if I put -2 here, I would just get that, right? Like I would be excluding the last 2 letters from that.
Thanks, that makes sense.
Okay.
I have a question.
Yes.
So the first letter or the first character in a string is 0, right?
Yes.
So I'm looking on like the Mozilla, I don't know, I guess I can just copy this in the chat. And it's like, it's taking out the first letter, but then it's using 1 as the beginning index. And it shows that it would put out, I don't know what I'm missing here.
Let me see real quick.
So I'm like, wouldn't it just take out?
So this would basically, so if we do this, right, and we come in here, so it'd be 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So I would expect that I would get that. So basically he space mourn would be what that would return. Why are you grumpy though? String 2. Oh, because there's a comma up here. There we go. So if we do console.log str2, right, he mourn, right? So we start counting here, right? So we start counting at the 1 position, which is that H. The T is the 0, right? So if I change that to a 0, we'd get the mourn, right? But by 1, we're skipping that T, and we're including everything up until this is the first letter to exclude, right? And A is I. So everything after I is going, I included is going to be excluded.
That makes sense. I think I just had like a brain fart. Yeah, sorry.
No problem. And so in the same thing, like, and so like if I just did 0, that would give me the whole thing, right? I start counting at 0 and I never stop. If I did 1, right? So then I've got he morning is upon us. And same thing, if I give it an end of -1, right, I'll chop off the last letter, which is the period. And then same thing, like I could do 2 and -2, right? And then I got rid of the TH and the S period at the end. And you can keep going this way and you're chopping things off the end, right? And or I could say 3, 4, right? And all I would get is a space. So that was a bad example. Let's look at 4, 5, and that should give me M, right? There's the M. So 0, 1, 2, 3, 4. Start counting, stop counting, and start excluding at 5, right? So basically I ignore this, I get to number 4, I count it, and I get to number 5, and including number 5, I stop counting, I exclude the rest of it, and that's how I just get the M over here.
Thank you.
And these are something where, like, when you're doing a challenge, even if you get if you get it wrong the first time, like, I mean, I've even like prefaced that a couple of times, right? Like before I ran the final solution, hey, I don't know which side this needs to go on, right? Or I don't know that this is the slice that I'm looking for, but I don't get charged money every time I hit the run button. So run your code, see if you did it right, see if you did it wrong, and then adjust from there, right? Like you don't have to, I mean, like for the application for Code Platoon or really any coding challenge, you don't ever have to get it right the very first run, right? Like if you're doing the free code camp and you run it and your tests fail, you just change what you need to change and you run it again. And you can use the tests to help guide you and see why you're failing. Excuse me. Yeah, for sure. You could, with that one, with the evil olive, we could probably like run a strip on that, I think. Well, let's see here, remove wait space from string. Yeah, so with a dot replace would get rid of all of it, right? So we could look at doing, let's see here, Palindrome. So I don't even know if we need to do anything where we reassign it. We might just be able to do word dot replace like that. Let's see here. So evil owl is the last one. No, it's still returning false. I do replace right. So let's take a look here. So word dot replace didn't do what it promised to do. Let's do this. String replace method returns an, okay, so it returns a new string. We could then do word equals word dot replace. Let's try that. There, now we're getting true. So there's our evil olive. It doesn't matter that it runs through that way each time, because there's just no spaces after the first time that it runs. So we could do world's longest palindrome, which is like some Scandinavian village, Finnish. For a dealer in lye, caustic soda. Still true, right? And so then we see how we're doing it, right? Like we're passing it down, we're comparing, we're shaving off the letters each time. And once we get there, and we're going to return that true all the way back up. All right. So it's 8:43. That's probably about it for this evening. We've recursed all we can recurse. As far as like opening up a new challenge at this time, but are there any other questions that I can answer about anything? Yeah, there you go. Words to live by, recursion, not even once. So is there anything else that I can answer for you related to tonight's stuff? Anything so far in the course? Anything software development related? Happy to take all questions.
So for the recursion, you said there's 2 returns that have to be, would we ever have anything where there's gonna be like more than that?
Yeah, I mean, technically you can have like theoretically you can have an unlimited number of recursive calls, right? But you're limited by the memory of your machine typically, because eventually you, even like if you've got a brand new like M1 Mac, like you can do enough recursive stacking to basically suck up all the memory the machine will let you have, and it'll tell you no more, right? And it'll stop working. And where recursion does happen, like I said, is like data science. So I'll drop this in here too. Has anyone ever heard of Minimax? So Minimax is a game theory algorithm. I had to do it as part of my apprenticeship at A-Flight. And we had to do it with tic-tac-toe. And basically you build an undefeatable tic-tac-toe game. And what it does is Minimax actually plays every single move in the game of tic-tac-toe, right? So you put, it doesn't matter if the computer goes first or if you go first, it basically will, and I think because it's like a 9x9 grid, Minimax tic-tac-toe number of moves. But I mean, basically, it's like I'm trying to think of like the total move count is, I think like the most it has to iterate through is like 27 or 81 different decisions. Because it has to account for, it basically it plays every single game that it can, So the first time it plays through, it starts with it putting the X in the top left corner, and then you putting an O in the middle top, and then it putting the X in the top right corner. But it goes through every single permutation of every single game that it could do. And so when it, like on a brand new Mac, it would take like 2 or 3 seconds for the computer to make the decision. But like mini Macs, you cannot use it to play a game of chess. Like there isn't a computer powerful enough to run it through a full game of chess using recursion, because it's like how many possible combinations in a chess game. Right. So after the 3 moves, you're 121 million possibilities deep. Right. And we don't have the raw computing power to do it. Like, and this was, if anyone's interested, there is a really cool documentary called AlphaGo, which is basically Google's answer to Deep Blue. They made a documentary about it, but like for however many permutations there are in chess, like it's infinitely worse in the game Go. And basically IBM was able to be like chess grand champions like in the late 80s, early 90s by taking a computer like the size of a warehouse and using it to compute, like brute force compute chess possibilities. And Google basically did AlphaGo to demonstrate that kind of like software is the future, that on a limited hardware set that they were basically able to increase the efficiency of software. And like AlphaGo was like the first computer program to ever beat like a Go grandmaster. And it just happened within like the last 5 years or whatever. And that was kind of like one of the last hurdles of like gaming AI. But so we talk about like tic-tac-toe where there's only 9 squares on the first move, to like a chessboard, I think there's like 144 or something like that, 12 by 12, to like a Go board is like 25 by 25 or 30 by 30 or something like that. So like you start running into like there's more possibilities or of a Go game playing out in all these different permutations than there are like stars in the known universe. All right, so that is that. Any other questions? Anything else you want to talk about?